Okay, let's think about another example here. So suppose that you are a professor. So you have to choose one student for the Academic Excellence Award, and the criterion is their grades. So suppose that there are two candidates, two finalists for the award, and you get their grades from 10 courses in economics. So you'd like to compare their grades and determine who's better, who's who performed better academically. And so the problem here is that the outcomes are not numbers yet. So then the problem here is you cannot compare which is larger. So in principle, the A and B cannot be compared. You can compare them only when you assume that they are like ordered, right? A is better than B. That means already they are some kind of numbers. Anyhow, you cannot add or subtract, or you cannot do any operation on those letter grades. They are not numbers. So first thing you need to do to compare these two students is to turn their letter grades into numbers. So now these outcome as it's automatic, so you know how to do it. So A minus turned into 3.7, A flat turned into 4. So then now you can compare and you can add and multiply them, and you can handle them as numbers. And now you make a random variable. You make them random variables. So you get random variable for the first student and another variable for the second student. Now let's summarize the data. So if from this table, it's just a bunch of numbers. There is no information. It's not informative. You cannot tell who's better. It looks like both are pretty good, but it's not easy to see who's better. And so we have to summarize the data, and the simplest way, the first step to summarize the data is to make a frequency distribution table. And in in this summary, so the first student got 1A and 4A minus and 3B pluses and 2B. And the second student got more A flat, but he got more B minus. So had more good grades, also more bad grades, like bad in terms of them. In the, so even if we summarize the data into a more compact table, still it is not clear who's better, right? Depending on how you compare them, you can it's not clear who is better than the other. So we are going to make a histogram. This is another way to summarize the data. And exactly, I turned this table, frequency distribution table, into histogram for 2.7 for each letter grade, like B minus, B plus, A minus, A. I count how many courses, how many grades they got, how many number of each grade, and two B minuses and one B, and two B, two B plus, two A minus, and three A. So that way, it shows a histogram. But the histogram still it's not informative. So it's higher here. Blue student 1 has a higher frequency in this area, but low here and low here. What does it mean? Like it's not easy to see what's going on. And then to read it like so, let me just explain what happened. So the outcome gets larger. The creator outcome go like this in a histogram, and the vertical axis shows frequency. You may replace the frequency into probability. The shape does not change. Basically, probability is calculated based on the frequency. So this is how we interpret a histogram, but it does not show you who's better. The main reason why it's not easy to tell is because what we are doing here is we want to have one number to compare them, to summarize them. So we would like to summarize the first student into one number and the second student into another number, one number. And then we'd like to have a one-on-one comparison. That's ideal. When you have more than a single number or one number, then the comparison becomes more tricky. So here comes the average. Average resolves all the problems. So we need, as I said, we need one number that represents each student. And usually we use GPA, right? GPA is exactly the average of those grades. So if you calculate the GPA, student 1 has higher average. So based on the average, student 1 is better. It's not it's not a perfect comparison. There may be some misleading points in there, but obviously this is the most common way to compare these two students. So even if it cannot be perfect, but it's maybe I think the most likely to be perfect. So then what else would you use? Then there are some alternatives, but it's hard to beat, hard to ignore average. So always average is a very powerful, simple but powerful tool to summarize data, and as a result, it makes your decision better and easier, right? So it simplifies your decision. And by the way, so we use the average as an example. I told you average summarizes the data into one number, but there may be it doesn't need to be on average as long as it represents the data. So that in general, we call such a measure as a measure of central location. So what we are interested is the location of the center, right? So the orange, the second student, has a center around here, but blue has a center around a little bit to the right. So the center is measured by the average, but it doesn't need to be on average, right? So in that sense, we are going to generalize our view from so the average is important because it is the most famous, most popular measure of central location. So there may be other measures for central location or central tendency, but uh, the average is the most widely used. And let me define the measure of central location. It is a value around which data are located. It's simple, like exactly what it means. And you may interpret it as a typical or representative outcome. So what is a typical grade from the student, right? So th- the average stands for such a value. It's a very strong candidate for the center. But later, we are going to learn the most the powerful alternative, median. So median is a strong alternative to the mean, and so we will learn about the median after we learn the mean, and we are going to learn what's the problems of using the mean, and then how the median can complement the problems. So okay, So let's define. Let's fix the terms. So usually the average. So far I called it the average, but it is pretty casual. So average is a casual way to call this, but in statistics, a more formal name is the mean. Mean is what we call this kind of measure. Basically, they are the same thing, at least in this course, right? And even more general and mathematical and theoretical term is expectation or expected value. Maybe in this course, I'm going to call this expectation because I'm more used to this term. So when I learn statistics and in most statistics textbooks, like higher level textbooks, statistics, expectation is more common than the mean. So I'm going to use the term expectation. And its notation also goes with expectation. So E of random variable x denotes the expected value of a random variable x, right? So E of x. So I'm going to call this expectation of x. So, but anyhow, in this course, these three terms are the same thing. You may like interchange between them, whatever, as much as you want, and in this course. But just I'd like to tell you the subtle differences among them. Okay, then let me show you another example. And uh, here, think about a lottery. Here, suppose there is a lottery with a $100 prize, and you get the prize with 1%. The other 99%, there is no prize. You just nothing. So then, in this case, there are only two possible outcomes: zero or $100. So the expected prize from the lottery is $50 because it's either zero or 100. So the average is $50. Is that right or not? So I'm going to answer this question in the next video. See you there.